Hey everybody, this is a lecture on wave behaviors. This is the second lecture on waves. In this we're going to discuss wavefronts and rays, interference, reflection, diffraction, and refraction. So let's get right started. So first of all, we have already seen one-dimensional waves, like waves on strings, but waves can be 1D, 2D, or 3D. A laser is something like a one-dimensional wave. It only travels in one direction. 2D waves can be found on the surface of a pond. Ripples will travel out, spread out in 2 dimensions on the surface of the pond. We could also have 3D waves. Radio signal spreads out in 3 dimensions. Sound waves through the air travel out in 3 dimensions, and even the turns out electron orbitals are 3-dimensional waves. Here's an example of a 2-dimensional wave right here. This would be an oscillation in maybe the surface of a pond, and you can see how the waves spread out and they form these almost circular shapes around our initial oscillation. The wavefronts of a wave show us the shape of the wave, and on a transverse wave that is the crests. So let's actually just go through this slide. We can have all different types of wave shapes. Planar waves or plane waves have wavefronts that are straight lines or planes, and we can see some plane waves right here. Circular waves have circular wavefronts. If you drop a rock into a pond, the wavefronts spread out like circles. That's what we have down here. We can have spherical waves that have wavefronts that are spherical. If you have a speaker in an open field, it's going to create spherical or approximately spherical wavefronts. Wavefronts are always perpendicular to the wave velocity. So let's take a look at this circular wave down here. We can see each crest is circular, and we're going to draw yellow wavefronts on them. But as you know, those circular waves are going to spread out radially. So our velocity is radial, our wavefronts are circular. They're always perpendicular. Yeah, the yellow lines are the wavefronts on our transverse waves here as well, and our velocity is always perpendicular to that wavefront. At large distances from the source, spherical and circular wavefronts actually appear planar. So here we can see some spherical wavefronts coming out from a point source here. And as those waves spread out farther and farther, the curvature of those wavefronts gets smaller and smaller, or seems smaller and smaller. So at very large distances, these spherical wavefronts appear planar. Wavefronts can also be bent by obstacles or by entering new materials. This shows us a lens taking some planar waves and bending them towards a point. Rays are arrows which show the direction of motion of our waves. And rays are always going to be perpendicular to the wavefronts. So here we have our wavefronts in red moving to the right and then being focused to a point, and our rays show us the direction of motion at all points. We're going to use both wavefronts and rays at different points and often together to show us kind of the general motion of the wave. And this is how a lens actually works, by bending our rays or by bending our wavefronts. Rays are always parallel to the wave velocity and therefore perpendicular to the wavefronts. Longitudinal waves also have wavefronts and rays. Here is something like, it's a circular oscillator going back and forth. And we can see the compressions and rarefactions spreading out circularly around our oscillator. For a longitudinal wave, the wavefronts are drawn at successive compressions. So if we pause this, we can see there's a compression here, a compression here, a compression here. Those are going to be our wavefronts. If we went back in time. So here we have some wavefronts drawn on our longitudinal wave. And our rays tell us the direction of motion of the wave, always perpendicular to our wavefronts. Okay, next up is wave interference. Waves are interesting. Now, matter you can't normally put normal matter basically you can't take a ball and another ball and stick them in the same place at the same time. That's not true with waves. Two or more waves can be in the same place at the same time, and when they overlap, we get this thing called interference. So when two waves occupy the same place, we use the principle of superposition to figure out what the resultant wave is going to be. Basically, we add the heights of the two waves that are overlapping to find the resultant wave. So there's two types of interference. There's constructive and destructive interference. Constructive interference is what you get when two waves have the same sign and then they overlap. Here we have two negative waves, and when they overlap they produce this green negative wave. Since the amplitude of this first one was -1, the amplitude of the second one was -1, the amplitude of the resultant wave, what we actually see, is going to be a pulse of -2, just for the moment that they overlap. And we can also see this down here. When these waves overlap, we get an amplitude of double the original pulse. So for constructive interference, the resulting amplitude is greater than the sum of the two contributing amplitudes. We get a bigger wave, basically, because our starting waves are the same sign. With destructive interference, we have opposite sign waves, and so they cancel. Here we have a wave of +1 and a wave of -2. So we're going to add those two amplitudes up, and we'll get a wave of -1. Our resulting wave is -1. We can see that here. Well, this is going to be some negative constructive interference. But when our sim starts over, when our GIF starts over, we'll be able to see that destructive interference. Oh, we got to watch that constructive interference one more time. Still pretty cool, though. Okay, so we have a wave of +0.5 and -0.5 right when they're overlapping. Our string is not disturbed at all. Our particles were totally flat. We had an amplitude of 0, just for a brief moment there. So that's destructive interference. Waves cancel. So here's an example. We have two waves that are overlapping, and it shows us the two waveforms that are overlapping. Let's label C for constructive interference, D for destructive, and then predict the resultant wave. And to find the resultant wave, we're going to use this principle called superposition. It's the same principle we use for adding vectors. All we got to do is add the displacements of the two waves that are overlapping to find the resultant wave. So let's just look at the letters. At G, we have two positive waves, so that's going to be constructive. They're going to add. And let's find the resultant amplitude. This is an amplitude of 4. This is 1.5, so our resultant is going to be 4 plus 1.5, 6.5. I'm going to label a dot there. At H, we have a positive and a negative wave. That's going to be destructive. They're going to cancel. -4 and +1.5 is going to give us an amplitude of -3.5. At I, positive and negative, that's destructive. +4, -1.5. That's going to be 4 minus 1.5, somewhere around here. At J, -1.5 and -4. That's going to be constructive. They're going to add two negative waves. That's going to be -6.5, something like this. And we can do that all the way down. I'm just going to go right here. 1.54 is 6.5. About. That's right here. Let's look at K. 1.5, -4, that's -3.5. That's destructive. L, it's also going to be destructive. 4, -1.5. Right here. M, it's going to be constructive. Something like this. N, constructive. Something like this. And O, destructive. Something like this. So we're going to get a wave that looks, this isn't going to be exact, but it's going to be something like this. As these waves are overlapping. And the more points I actually sample, the more points I actually add up, the more accurate my new resultant waveform is going to be. But this is all we do. We just add the amplitudes of our waves to find the resultant amplitude. Interference is probably actually the most interesting effect of waves, and it causes all kinds of interesting phenomena. It creates these things called standing waves, where the waves don't look like they're moving, and this is actually what allows musical instruments to produce different notes and different tones, because we only get certain waves that can form on a string or in the cavity of a wind instrument, and that's because of the way these waves interfere. There's also this thing called beats in music, or in audio, really in any wave, where the tone will get loud and then really soft, and then really loud and then really soft at repeated intervals. We might talk about that later. DVDs and CDs and Blu-rays all rely on interference of a light wave in order to read data. We already mentioned electron orbitals are waves. They're also caused by interference. In concert halls, some places are going to be loud and some places are going to be quiet, just because as that wave travels around, it's going to interfere. In some places it'll cancel, some places it will add. Anti-reflective coatings on lenses cancel out reflected waves so that you don't get reflection. And here's just a soap bubble. We get this rainbow of colors because at higher up on the soap bubble it's thinner, and so we'll get some wavelengths that cancel out in some places and some wavelengths that don't cancel out. And so we get these different colors. For light, the wavelength is the color. So interference is pretty darn important for waves. Let's take a look at a few other effects. So waves can travel, and they travel through a medium at a constant speed, but they can also interact with boundaries. When they interact with a boundary, they can reflect, they can be absorbed and dissipate their energy, or they can enter into the new medium. The boundary is just going to be where one medium ends and a new one begins. Now, when a wave enters a new medium, we know that the wave's speed depends on the medium. So if it enters a new medium, the speed changes. But since the frequency is constant, since the particles at the boundary are vibrating at one frequency for both media, then by V equals lambda F, if our frequency is constant and our speed changes, then our wavelength also has to change. So when our wave enters a new medium, that speed changes and we get some interesting effects. Reflection is what we get when a wave strikes a boundary and is reflected back. Here we can see reflection on one end. Notice that the wave reflected and stayed upright. The wave can also reflect on the left end, and it will actually flip. It inverts. On fixed boundaries, a wave will invert, and on free boundaries, the wave does not invert upon reflection. That's not going to be super important right now, but it is going to be important later when we're talking about different types of standing waves and different types of interference effects. This little diagram over here shows us how rays reflect off a curved parabolic mirror. This is a concave mirror. Concave mirrors can be used to focus images, and they're used a lot in telescopes. Refraction is what occurs when a wave enters a new medium at an angle. So when our wave enters a new medium, we know that it changes speed. And when our wave speed changes, that actually changes the angle of the wave fronts and therefore the angle of the rays. So this shows us two rays of different color light and from air entering into glass, bending, that is refracting, and then when they leave the glass, they bend again, they refract again. Different wavelengths are bending at slightly different angles. You've seen refraction anytime you look in water. You get effects like this, where this straw looks like it's broken or it looks like it's bent, even though we know it's a straight straw. So let's use this Falstad Ripple Tank app to take a look at refraction. Let's get rid of these. Here we go, refraction. So we're sending a plane wave in. And notice a plane wave comes out in our new medium. Let's up the brightness a little bit. Plane wave comes out in our new medium, but the angle of the wavefronts has changed. So therefore, the direction of our wave has changed, and we get a wave that bends from this direction to this direction. That's all refraction is. Diffraction is what we get when a wave meets an obstacle, either a slit or an opening. Basically, when a wavefront hits an obstacle, and you can see it in this diagram, it spreads out like this. So let's take a look at diffraction using this ripple tank applet. Let's just look at an obstacle. This is just a little obstacle in the way, and notice that our waves spread out in these kind of circular shapes around our obstacle. Let's see if we can do a slit. I'm gonna clear the waves. So we're sending plane waves in, and yet when they go through the slit, they spread out in this kind of circular shape. And that's wave diffraction for you. It happens at any obstacle. We actually get maximum diffraction when our wavelength is about the same as the size of the obstacle. So I'm going to clear the waves, change the wavelength. Notice we have more intensity of our waves spreading out now. It's darker. Maybe not, actually. That was interesting. I think we're actually getting some interference effects because our wave is getting brighter and darker. I think it's bouncing against the back wall and interfering with itself. That's quite cool. This is a very high quality simulation. But anyway, waves spread out behind obstacles. So in summary, wavefronts show the shape of a wave, rays show the direction of motion of a wave. Wavefronts and rays are always perpendicular. When two waves overlap, they interfere, and the resultant wave is found by adding the displacements of the overlapping waves. That's called superposition. Reflection is when a wave bounces off a boundary. Refraction is when a wave enters a new medium and changes direction because of that change in speed. And diffraction is when a wave spreads out behind an opening or obstacle. That's all. Hope that's helpful. Bye.